So, my dear students, so let us continue the last session, that is the coordination compound. So, now today we are going to discuss the another the valence bond theory, VBD theory for the octahedral complexes. So that we already completed in the tetrahedral complexes and also the square planar complexes. But now we will see the octahedral complexes. So you have already completed the tetrahedral and square planar. So this is also exactly similar, but there is something different between this octahedral and the square planar and tetrahedral. So what actually this is see here. So first, generally these are the two types of octahedral complexes are there. So I already told you that if it is a tetrahedral, then the hybridization will be definitely sp3. Then if it is square planar, then it is dsp2 hybridization. But if it is octahedral, what is the geometry here? After octahedral means definitely six ligands are there. Then what actually the geometry, that is sp3 d2 or d2 sp3. So here we are having two types of hybridizations are there. One is sp3 d2 and another one is d2 sp3. What actually difference between these two here? So see here, sp3d2. So here how many hybrid orbitals are here? So here s1 and here 1, here 3, that means 4, and here again 2, totally 6. And here also you can take here d2 sp3, 2, 1 and 3, totally 6. So this is also 6 and this is also 6. Here sp3d2 and here d2 sp3. There are two types of hybridization. Both are actually same, but actually there is small difference. Here d2 here after the sp3 is there, but here the D2 is before the sp3 hybridized orbital is there. So what actually difference between this I will tell you here. And here in case of tetrahedral, the hybridization will be sp3 and the square planar will be dsp2. So let us understand the octahedral complexes with the hybridization. So let us see here. So let us continue. So mostly generally the D2 sp3 and sp3 d2. So just understand, just remember this point here. So d2 sp3 actually they are called inner orbital complexes and sp3 d2 they are called outer orbital complexes. So why, what is the reason actually why it is called octahedral and why it is called outer orbital and why it is called inner orbital, I will tell you here. So first you should understand one thing here. So if you don't understand this thing, please see the whatever the before videos, because you should understand here the strong field ligands, and the another one is weak field ligand. So weak field ligand. So you should understand these two concepts here, strong field and weak field. So that means what are the strong field ligands? So what are the weak field ligands? You know that generally the all the halogens and H2O and NH3 generally it is a weak field ligand with the 3D series. With 3D series. So 3D series ante that means scandium to zinc. So scandium నుంచి zinc వరకి the metals, so whatever the metal, if it is coordinated with these ligands, that is all halogens like fluorine, bromine, iodine, and water and ammonia, all are generally they are weak field ligands. But in case of strong field ligands, that is 4D series and 5D series, for 4D series and 5D series, all ligands are strong field ligands, and for the 3D series, especially cyanide and CO, so some of the specific ligands are strong field ligands. So that I already told you in the last video. So please see that particular video, then you can easily understand this particular VBT theory for the octahedral complex. So first you should understand, see here. So here sp3d2 and d2 sp3. What actually difference between this d2 sp3? So once again I will write here d2 sp3 and another one is sp3 d2. So what actually difference between these two here? So you can understand here. So I will write here like this, n minus 1, n minus 1 d2 ns np. And here I will write ns np and I will write nd. So why I am writing here and why I am writing like this, np3 and d2, and here also np3. So what actually difference between this? So nothing but, so actually the d, mostly the 3D series. So let us understand. I will write these things like this, 3d2 4s and 4p 3. So here I will write like this, but here I will write like this, 4s 4p 3 and 4d 2. So what actually difference between these? So the hybrid orbitals, whatever the hybrid orbital, the atomic orbitals, they are hybridized to get an equal energy. So the hybrid orbitals are. So what is actually difference between these two here? So the hybrid orbitals present in sp3d2 all are in the same orbit. Here you can observe here 4 4 4. That is same here, n. So all are only same orbital. So the hybrid orbitals are only participating only in the fourth orbit. So whatever may be nth orbit. But observe here d2 sp3, d అనేది ముందు వచ్చిందంటే, so whatever the d orbital which is before the fourth orbit. So you can observe here 3d2 4s2 4p3. That means here n minus 1, I will write, I have already written here n minus 1 d2 ns and np3. So what actually difference between this? So n minus 1 d is there, that means it is also undergoing hybridization to form the octahedral geometry, but the difference is the d, whatever the hybrid orbitals of d, which is lesser than the s orbital or p orbital. s orbital p orbital fourth లో ఉంటే దానికంటే ముందు థర్డ్ ఆర్బిటాల్ లో డి ఆర్బిటాల్ హైబ్రిడైజ్ అవుతుంది అని. అండ్ హియర్ బట్ ఈ sp3d2 అంటే అలా కాదు. ఇది 4s అయితే 4p 4d, ఇది 5s, ఇది ఫిఫ్త్ ఆర్బిట్ అయితే 5s 5p 5d. సో అట్లా వాటెవర్ మే బి 5s 5p 5d. సో వాటెవర్ మే బి హియర్ ఆల్సో ఇఫ్ ఇట్ ఈస్ 3d 4s 4p ఇలా కాకుండా 4d 5s, we can easily write like this. So we can write as 4d 5s 5p, we can write also like this, but here you can write like this 5s 5p and 5d. So you should write like this. And these particular complexes, whatever the complexes formed by the hybridization of d2 sp3 are called inner orbital complexes. They are called inner orbital complexes. So why they are called inner orbital? Because the orbital which is hybridized d, the d hybrid orbital which is inner, so it is called inner orbital complexes. And here these are called outer orbital complexes, that you should understand here. So now I have written already these two things here. So I have written inner orbital and outer orbital, both the complexes are different. So inner orbital complexes and outer orbital complexes both are different. So inner orbital complexes are nothing but d2 sp3. And how it is d2 sp3 you can easily understand later on. So here this is also outer means sp3 d2. And this point, remember this, mostly the inner orbital complexes are formed by the strong field ligands and outer orbitals are formed by the weak field ligands. So why I will tell you, see here. So let us understand. First I will take inner orbital complexes, then we will understand with the outer orbital complexes. So let us take with the inner orbital complexes first. So inner means, so what actually inner means? Definitely the hybridization must be D2 sp3. So the hybridization must be D2 sp3. So let us understand here how it is D2 sp3 here. So let us take this particular complex here. So we can write these particular complexes, that is FeCN6 FeCN6 minus 4. So minus 4 means you can write here as K4. There is no problem. So if you write K4, remove this. So you can write like this. You can remove like this. So there is no difference between these two here. This one and this one. There is no difference here. Because in place of K4, I am writing minus 4 here. So here potassium, you can write any, you can take like sodium also. Sodium 4 and you can write CN6 like this. You can write like this also. What, there is no problem here because sodium which is plus 4 and definitely it is -4. You can write like this also. But see here, you can understand here what is actually the name of this complex here. So this is an anionic complex. There is no cation to write before actually. So first cation rayali, but there is no cation here. So you can directly write the anionic name. So that is hexacyano. Six cyanyl ligands are there. So each anion is having the suffix O. Hexacyanoferrate, because it is an anionic complex, ferrate 2 ion. So you can easily calculate like this 6 minus 4, you will get plus 2. The charge of the metal is plus 2 here. So hexacyanoferrate 2 ion. So let us understand the whatever the hybridization, what is the structure of this particular geometry, this particular complex here. So let us understand first. So what actually the central metal, which is iron. So you should remember the again the D black elements. So you should remember the D black elements. Then only you will understand all these things, the hybridization. So you can understand all these things. So see here, I will tell you once again the hybridizations of them. So see here, once again I will tell you here, see here, again the scandium, which is 21, 22, 23, 24, 25, 26, like this you should remember these 10 elements. So here 21 means definitely it is 3D1 4s2. 22 means again 3D2 4s2. Here 23 means here again 3D3 4s2. Here only the chromium and copper will be exception. And again here 25 means again 3D5 4s2. 26 means again 3D6 4s2. So here 27 means again 3D7 4s2. So 28 again. So 3D8 4s2. Again the zinc, which is 3D9 4s2. But in case of copper, so in case of copper, that is the exception. Actually it should be 3D9 4s2. Actually it should be like this, and here also it should be 3D4 4s2. It should be like this. So but actually it will get like this 3D5 4s1. This is the correct. Actually this is completely wrong. And here also 3D9 4s2, it is actually 3D10 4s1. So this is very important here. So you should write the electronic configuration of these elements from scandium to zinc. So here we are having the complex which is iron. So iron, which is 26, that is 3D6 4s2. So let us understand these things here. So see here. So here the iron, which is 26 here. So see here. Iron, here generally the 26 here. 26 means you can write here 3D6 4s2, 26 here. So 3D6 4s2. Just now only I told you here how to write the electronic configuration of iron here. So you should write the electronic configuration like this. So see here. So 3D6 4s2. So 3D6, so see here 3D6 and 4s2. So then electronic configuration of iron, that is Fe plus 2. So what is the charge of the iron here? So you can easily, what is the charge here? So the charge of the iron, which is plus 2 here. You can see here the 6 minus 4, you will get plus 2. Or else you can calculate the oxidation state like this. So I already told you many times. So how to calculate the oxidation state? That is x plus 6 into minus 1, because cyanide is having the oxidation state -1 and this is -4. Then you can write like this: x minus 6 is equal to -4 and x is equal to -4 plus 6, and you will get plus 2. In this way you can calculate the oxidation state of iron, which is plus 2. That means it loses 2 electrons. So first it is 3d6 4s2, and it will lose 2 electrons. That means 4s2 electrons will be removed out, the remaining will be this. Now electronic configuration in the ligand field. So whatever the ligands here is cyanide. So cyanides ఉన్నప్పుడు electronic configuration ఏమైతుంది? So what happens? So I already told you the weak field ligands and strong field ligands. So if it is weak field ligands, so what happens here? And if it is strong field ligands, so strong field ligand, స్ట్రాంగ్ ఫీల్డ్ ఉన్నప్పుడు ఏమైతుంది, వీక్ ఫీల్డ్ ఉన్నప్పుడు ఇట్ విల్ ఫాలో హున్స్ రూల్. But in case of strong field, it not follows Hund's rule. It not follows Hund's rule. So what are the weak field again? I already told you that is all halogens H2O and NH3. But strong field again, the cyanide and CO, the CO, carbon monoxide, and many ligands are there. But mostly we'll get only 2 or 3 ligands, so that you can easily remember those things here. So listen, understand here. See here. So again, so let us understand here the complex which is cyanide here. So remember that cyanide, NO2, En, so CO. These are all the strong field ligands. These are all strong field ligands. So in case of strong field ligands, so it doesn't follow Hund's rule. Hund's rule follow up ఏమైతే నాన్న, Hund's rule అంటే ఏం లేదు నాన్న. ఇప్పుడు ఎలక్ట్రాన్స్ ఇలా ఉన్నాయి, ఈ ఆర్బిటాల్లో ఇలా నిండుతుంది. So like this. So I will show you how it follows Hund's rule. So Hund's rule అంటే ఏం లేదు, very simple. If the electrons are 6, so let us take if it is d6 ఉన్నాయి అనుకోండి, ఎలా నింపుతాం మనం, Hund's rule ఫాలో అయితే ఇలా నింపాలి 1 2 3 4 5 6, and this is our Hund's rule. దాన్నే మనం Hund's rule అంటాం. అంటే no 2 electrons can enter into a same orbital at a time. ఒకటేసారి 2 ఎలక్ట్రాన్ రాయకూడదు, మొత్తం ఫిల్ అయిన తర్వాత మళ్ళీ మొదటికి రావాలి. ఇది Hund's rule. Hund's rule కి ఆపోజిట్ ఏంది అంటే మొత్తం ఫిల్ కాకముందు ముందే రాయొచ్చు. ఎట్లా 1 2 3 4 5 6. సో ఇది d6 అయితే. ఇప్పుడు దీనికి డిఫరెన్స్ ఏంటినా, Hund's rule అనేది దీనికి డిఫరెన్స్ ఏంటన్నా, సో దిస్ ఇట్ ఈస్ Hund's rule. ఇదేంటన్నా, Hund's rule ఫాలో అవ్వకపోతే దిస్ ఈస్ అగైనెస్ట్ Hund's rule. సో దట్ యూ షుడ్ రిమెంబర్ దాట్. సో ఇన్ కేస్ ఆఫ్ వీక్ ఫీల్డ్ లిగాండ్స్, ఇట్ ఫాలోస్ Hund's rule. ఇలా ఫాలో అయిపోతేనా అంటే మొత్తం అన్ని నిండిన తర్వాత మళ్ళీ మొదటికి వస్తుంది. బట్ ఇన్ కేస్ ఆఫ్ స్ట్రాంగ్ ఫీల్డ్ లిగాండ్స్ అలా కాదు, మొత్తం అన్ని ఒకే దగ్గరనే ఫస్ట్ నిండిపోతాయి, ఎన్ని ఉన్నాయో అన్ని దగ్గరకు వచ్చేస్తాయి, మొత్తం అన్ని ఒకటి దగ్గరకు వచ్చేసాయి. So see here, so let us understand these things here. So first it is cyanide. So cyanide definitely it is a strong field ligand. So it doesn't follow Hund's rule. So Hund's rule follow అవ్వదు. ఏమైతే చూడన్నాను ఇక్కడ ఎన్ని ఉన్నాయన్నా, సో ఎన్ని ఎలక్ట్రాన్స్ ఉన్నాయి 1 2 3 4 5 6. సో ఇక్కడ ఏమున్నాయన్నా 4s2 అయిపోయింది. సో బికాస్ 2 electrons are removed out, so the remaining will be 3d6 ఎలక్ట్రాన్ నింపాలన్నా. సో Hund's rule ఫాలో అయితే ఇలా రాయాలి, this is according to Hund's rule. But it is a strong field ligand. So it doesn't follow Hund's rule. So 6 electrons అలా నిండకుండా ఇక్కడ నిండిపోతాయి 1 2 3 4 5 6 ఇలా అక్కడే నిండిపోతాయి. అదే Hund's rule ఫాలో అయింది అనుకో అలా ఉండదు, ఇట్లా నిండుతాయి 1 2 3 4 5 మళ్ళీ 6 మళ్ళీ మొదటికి వస్తాయి. సో దట్ ఈస్ Hund's rule. బట్ ఇన్ కేస్ ఆఫ్ దిస్ పర్టికులర్ కాంప్లెక్స్, దిస్ ఈస్ అవర్ స్ట్రాంగ్ ఫీల్డ్ లిగాండ్. దిస్ ఈస్ ద స్ట్రాంగ్ ఫీల్డ్ లిగాండ్. సో అందుకే ఇవన్నీ అట్లా నిండకుండా మొత్తం అన్ని దగ్గరకు వచ్చేసాను. 6 ఎలక్ట్రాన్స్ ఫస్ట్ నిండుకుంటూ పోతున్నాను. సో యూ విల్ గెట్ లైక్ దిస్. 6 ఎలక్ట్రాన్స్ ఈడికి వెళ్ళిన తర్వాత ద రిమైనింగ్ ఆర్బిటాల్స్ విల్ బి లైక్ దిస్. అబ్జర్వ్ హియర్. సో అబ్జర్వ్ దీస్ ఆర్బిటాల్స్. You can observe here. So what actually orbitals here? So this is our 3d and this is 4s again. This is 4p here. We are already written here 3d6 4s2. This is 3d 4s and 4p. So how many vacant orbitals here? So 6 vacant orbitals are there, in which d2 that is a 3d2 and 4s in fourth orbit, that is s orbital, and again fourth again the p orbital. Here it will undergo d2 sp3 hybridization. Why? Because we are having 6 cyanide ligands. So there are 6 cyanide ligands are there. So these 6 ligands, so each ligand, whatever I already told you that a ligand will donate its 2 electrons into their vacant d orbital. Hence it is called our complex. So here each ligand will donate its lone pair of electron to empty orbital of metal d black d orbital. Here each ligand, each cyanide, each ligand, which will donate its lone pair of electron into this vacant orbital like this. So it will donate its 2 electron like this. ఇలా డొనేట్ చేస్తాను నేను, ఇలా ఇక్కడ డొనేట్ చేస్తుంది. సో ఈ బై లైక్ దిస్, ఇలా in this way it can form like this. So ila manaku form chesena. Then the hybridization will be finally will get the D2sp3 hybridization. So ఈ remaining మనకి ఇక్కడికి వచ్చినాయి కదా, దీని ఏమంటాం మనం D2sp3 hybridization. And remember that it is 3D 4s, so that is 4p. So that you should understand here. This is the inner orbital complex. So this is the inner orbital complex here. So why? Because you can observe here this. So here it is producing D2sp3. Here it is D2sp3, but it is not sp3d2. It is not producing the sp3d2 hybridization. sp3d2 వస్తలేదు hybridization. మనకి ఏం వస్తుంది అంటే D2sp3 వస్తుంది. Hence it is called inner orbital complexes. Inner orbital complexes. So what actually the structure of this? So definitely if it is 6 ligands ఉంటే ఏమొస్తాయన్న, 6 ligands ఉంటే ఎప్పటికీ కదా octahedral structure వస్తుంది. So octahedral structure. So this is our octahedral structure. So this is our octahedral structure. So I already told you in the last session, that is, so you have already seen the octahedral structure like this. So these are all the octahedral structures. So these are all octahedral structures. So you know that these are all octahedral structures. Oh, so these are all octahedral structure. You know that. So here four ligands are there. So here four, whatever the four ligands are there, and upper one and lower one. So see here, this is our octahedral structure. So this is our octahedral structure. So each, whatever may be, all our octahedral structure, the hybridization will be sp3d2 or D2sp3. So if it is D2sp3, then it is called inner orbital complex. Inner orbital complex. And if it is sp3d2, it is called outer orbital complex. Outer orbital complex. So we will understand this. So we see now an example for the inner orbital complex. Now let us see some another example so that you can understand all these things. So let us take some another example. So let us, I will tell you, I will take another example so you can easily understand here. So let us take this particular example. So see here. So here the FeCN6 minus 3 here. So what is actually difference between the first complex? So first complex is FeCN6 minus 4 here. So what is the oxidation state of here iron? Simply you can take this 6 minus 4, you will get plus 2. So you know that this is the structure. What is the difference between the second one? So observe this. The second one. So the second one. What is the second one here? So here again, this is Fe. Here what? Here దానికంటే ముందు ఏముందన్న? So FeCN6 అక్కడ -4 ఉంది అన్న. ఇక్కడ -3 ఉంది. So what is the oxidation state of iron here? Simply 6 minus 4. 6 minus 4 you will get plus 2 here. But here again 6 minus 3 you will get plus 3 here. The charge, the oxidation state of iron is plus 3 here. Now let us understand this. So ఇప్పుడు అర్థం చేసుకున్నాం మనం. So let us take this particular complex. So this is also very simple and you can understand very well. See here. So what is the charge of the iron? 6 minus 3 you will get plus 3 and hexacyanoferrate 3 ion. So that you can study in the nomenclature very well. And now we'll see the further the hybridization of this. Is it D2sp3 and why it is D2sp3? Why not sp3d2? That we will understand here. So again, so iron, which is a central atom, having, I already told you that this is 26. 26 means 3d6 4s2, and then cyanide, which is a strong field ligand, so it doesn't follow Hund's rule. So that those rules are very very important here. And see here, next further you can see here. So let us take the electronic configuration of iron. So iron into the first electronic configuration 3d6 4s2. So this is our 3d6 4s orbital and this is the 4s orbital. And see here, this is 3d6 4s2 here, 3d6 4s2. And here the again electronic configuration of plus 3 here, the charge of the iron which is plus 3 here. So that you have already seen here. So see here. So what is the charge here? So you can observe here is 6 minus 3 you will get plus 3 here. So the charge of the iron which is plus 3 here. And now let us see here. So what actually see here? So we have to remove 3 electron. How can we remove the electron? How can we remove those 3 electrons? How can we remove those 3 electrons? అంటే ఎలా తీసేయాలి నాన్న? ఏం లేదు, సింపుల్. ఎలా తీసేయాలి అంటే సో 3 ఎలక్ట్రాన్స్ తీసేయాలి నాన్న. సో 3 ఎలక్ట్రాన్స్ తీయడం అంటే we are having actually 3d6 4s2 ఎలక్ట్రాన్స్ ఎలా తీసేది నాన్న? లాస్ట్ నుంచి ఎప్పుడు కూడా తీసేయాలి. సో లాస్ట్ ఇవి రెండు తీసేస్తాం నాన్న. సో లాస్ట్ కి ఇవి రెండు తీసేస్తాం. సో ఆఫ్టర్ రిమూవింగ్ దిస్ 2 ఎలక్ట్రాన్స్ రిమైనింగ్ విల్ బి 3d6. సో మనకు 3 కావాలి కదా ప్లస్ 3 అంటే ఇందులో నుంచి కూడా ఒక ఎలక్ట్రాన్ తీసేయాలి. సో నౌ యూ విల్ గెట్ ఓన్లీ 3d5. సో ఆఫ్టర్ రిమూవల్ ఆఫ్ 3 ఎలక్ట్రాన్స్ హియర్ 3 ఎలక్ట్రాన్స్ షుడ్ రిమూవ్డ్. సో ఫస్ట్ 3d6 4s2 ఉంది, ఇందులో 3 తీసేయాలి. సో 3 తీసేయాలంటే ఏముందన్న, సింపుల్ గా ఇందులో ఫస్ట్ 2 ఎలక్ట్రాన్లు ఇవి తీసేయాలి అండ్ ఇందులోకి వెళ్ళి ఇంకొక ఎలక్ట్రాన్ తీసేయాలి. సో రిమైనింగ్ విల్ బి 3d5. So 3d5 electrons should fill like this. Ante nana 1 2 3 4 5 it should fill like this. 3d5 here. So first ఏమన్నా 3d6 4s2 ఉంది and plus 3 ఉన్నందుకు మళ్ళీ 3d5 అయిపోయింది. సో ఆఫ్టర్ అగైన్ దీని తర్వాత ఏముందన్న మళ్ళీ in presence of ligand. So ligand ఎట్లాంటిదన్న, this is the cyanide. Cyanide I already told you that the cyanide which is a strong field ligand. సో ఇది హున్స్ రూల్ ఫాలో అవ్వదు అంటే అన్ని ఒక దగ్గరకు వస్తాయి. దే విల్ కంప్లీట్లీ పేర్డ్ అప్ టుగెదర్. సో ఇక్కడ ఎన్ని ఉన్నాయి నాన్న, 5 ఎలక్ట్రాన్స్ ఉన్నాయి. 5 ఎలక్ట్రాన్లు ఒంటరిగా ఒక్కొక్కటి హున్స్ రూల్ అయితే ఇట్లా కంప్లీట్ గా ఫిల్ అవుతాయి, అంతే నాన్న. బట్ ఇట్ డజంట్ ఫాలో హున్స్ రూల్. హున్స్ రూల్ ఫాలో అవ్వకూడదు ఎందుకంటే ఇది స్ట్రాంగ్ ఫీల్డ్ లిగాండ్. సో ఇట్ విల్ దోస్ 5 ఎలక్ట్రాన్స్ విల్ ఫిల్ లైక్ దిస్. సో 1 and 2 అక్కడ పోదు నాన్న, ఇక్కడ దాకా పోదు. సో ఇక్కడ నిలుస్తుంది 2 3 4 5 it will fill like this because it is a strong field ligand. If it is a weak field ligand, you know that the electrons will fill like this. Electrons అన్ని ఎలా ఫిల్ అవుతాయి నాన్న? సో ఎలక్ట్రాన్స్ అన్ని ఎలా ఫిల్ అవుతాయి? సింపుల్ గా 1 2 3 4 5 ఇట్లా ఫిల్ అవుతాయి. దిస్ ఈస్ హున్స్ రూల్. This is Hund's rule, but in case of strong field ligand, it doesn't follow Hund's rule. Hund's rule follow avvakudadu. They will completely paired up together, so it will form like this. So see here how many again vacant orbitals are there here. So here D2 sp3 here again the hybridization which is D2 sp3. So you can easily understand here. Here there is a vacancy. Again the 6 cyanide ligands will come here and it will make the dative bonds where with this 6 hybrid orbital like this. So here these electrons are donated by each cyanide ligand. ఇక్కడ ఒక cyanide ligand, ఇక్కడ ఒక cyanide ligand, and ఇక్కడ ఒక cyanide ligand, ఇక్కడ ఒక same cyanide ligand, ఇక్కడ ఒక cyanide ligand. So those 6 cyanide ligands are which will give those 6 electrons, 6 lone pair of electron into their vacant hybrid orbitals which are D2 sp3. Hence this is the inner orbital complex. This is our inner orbital complex. The hybridization will be D2 sp3 here. So I will ask you a question here. So when generally the inner orbital complexes are mostly formed by the mostly the inner orbital complexes are formed by the by the strong field ligand. Why? So ఎందుకు ఇన్నర్ ఆర్బిటల్ కాంప్లెక్సెస్ స్ట్రాంగ్ ఫీల్డ్ లిగాండ్స్ ని ఎక్కువ ఏర్పడతాయి నాన్న? ఎందుకు అంటే ఏం లేదు నాన్న, యూ కెన్ రిమెంబర్ సీ హియర్. ఇఫ్ ఇట్ ఈస్ స్ట్రాంగ్ ఫీల్డ్ ఏమైతే నాన్న, అప్పుడు అన్ని దగ్గరకు వచ్చేస్తాయి, అంతేగా నాన్న. సో డెఫినెట్లీ ఇప్పుడు ఉదాహరణకు 5 ఉన్నాయి నాన్న, ఇది స్ట్రాంగ్ ఫీల్డ్ అయింది అనుకోండి, హున్స్ రూల్ ఫాలో అవ్వకుండా అన్ని దగ్గరకు వచ్చేస్తాయి. అన్ని దగ్గరకు వస్తే ఏమైతే నాన్న, అప్పుడు ఇది వేకెంట్ అయిపోతుంది. సో ఇది వేకెంట్ అవుతుంది అంటే డెఫినెట్లీ ఇట్ కెన్ మేక్ అగైన్ D2 sp3 hybridization. So in case of strong field ligand, so it will produce like this. In case of strong field ligand, so you can easily produce the D2 sp3 hybridization. So let us understand if it is weak. ఇప్పుడు వీక్ ఉంది అనుకోండి, so that is a 3d here, it is 4s and it is 4p here. So if it is weak, ఇక్కడ సైనైడ్ లేవురా, నాకు సైనైడ్ కాకుండా నేను క్లోరిన్లు పెట్టినాం, బ్రోమిన్లు పెట్టినప్పుడు ఏమైతుంది మరి? సో ఈ 5 ఎలక్ట్రాన్స్ ఇలా ఉంటాయా? డెఫినెట్ గా అలా ఉండవు. ఎందుకంటే అది హున్స్ రూల్ ఫాలో అవ్వాలి. హున్స్ రూల్ ఫాలో అవ్వాలంటే ఇలానే ఫాలో అవుతుంది. సో ఇప్పుడు దీనికి ఇలా అన్ని దగ్గరికి రావు, పేర్డ్ అప్ అవ్వవు. అలాంటప్పుడు ఏం చేస్తాను? అవి అలానే ఉంటాయి. ముట్టకూడదు. మరప్పుడు 6 క్లోరిన్స్ ఎక్కడికొస్తాయి నాన్న? 6 క్లోరిన్స్ ఎక్కడికొస్తాయి నాన్న? మళ్ళీ 6 వేకెంట్ ఆర్బిటాల్ కావాలి కదా! సో, దిస్ 6 వేకెంట్ ఆర్బిటాల్ దే విల్ ఫిల్ లైక్ దిస్. So they will take extra 5 orbitals of this 4d orbital, and it can form again the hybridization will be like this sp3 d2, then it will form like outer orbital complexes. That I will tell you later. But you should understand, you should remember one thing here. If it is strong field, once again I am telling you that if it is strong field, ఇవన్నీ దగ్గరకు వచ్చేసాయి, they will pair it up together. It doesn't follow Hund's rule. That point you should remember, very very important here. That is very very important here. And now let us see the continuation of this. So I will tell you the another example. So we'll take many such example so that you can easily understand here. So I will take the another best example here, the CO. So this is also very very important here. So this is the exception here, and this is very very important. And the CO, which is NH3 here. CO again, what is the atomic number here? Again 27. So 27 means, again you know that the 27 which is 3d7 4s2 here. 3d7 4s2 here. That is a 3d7 4s2 here. Again the 3d7 4s2, that means that what is the charge of this cobalt here? So the charge of the ammonia which is 0, and here which is cobalt which will be a 0 plus 3. What is how much here? The oxidation state of cobalt again plus 3 here. So let us understand the VBT theory for this particular complex. So see here. So let us see this. So first cobalt here. So this particular cobalt is having the oxidation state as, sorry, the electronic configuration as 3d7 4s2. So see here, this is a 3d and this is 4s and this is 4p here. So 3d7 here. So the electrons will feel like this. So here you can calculate here, 7 electrons are there, 3d7 4s2. Now after removal of 3 electrons, here the cobalt which is having the plus 3 oxidation state. So plus 3 means how many electrons we should remove? 2 electrons. How can we remove 2 electrons? We should remove 2 electrons from here and 1 electron from here. So you will get directly 3d6. So 6 electron will fill like this. So the ligand, now what type of ligand here is there? If it is strong field ligand, the electrons will present like this. But if it is strong field ligand, then definitely the electrons will paired up together. So now we need to see the ligand which is strong field or weak field. If it is weak field, it follows Hund's rule like this. But if it is strong field, the electrons will be paired up together and it will form D2sp3 hybridization. So what type of ligand is there here? NH3 is there. NH3 is generally weak field ligand. Generally weak field ligand for the 3D series. 3D series లో ఏవైతే ఉన్నాయో, that is the scandium to zinc. Scandium నుంచి zinc వరకి all generally the scandium నుంచి zinc వరకు నాన్న. So scandium నుంచి zinc వరకు general గా ammonia is weak field ligand. But except there is a exception. There is a exception for cobalt. Cobalt. Remember this point, very very important. So ఒక cobalt కి నాన్న, for cobalt the NH3 is a strong field ligand. NH3 is the strong field ligand. Remaining all other 3D series, ammonia is also weak field ligand. So once again I am telling you that whatever the weak field ligand, weak field ఏముంటాయి నాన్న? All halogens and H2O. అంతే, పెద్ద అంత అంత గుర్తుంచుకోవడానికి అంత కష్టంగా ఏం లేవు కూడా. వీక్ ఫీల్డ్ గ్యాన్స్ ఏముంటాయి అంటే హాలోజన్స్, వాటర్, అండ్ దీంతో పాటు ఒక అమోనియా. అమోనియా ఎక్సెప్ట్ ఒక కోబాల్టిక్ మాత్రం ఉండదు. కోబాల్టిక్ ఒక్కదానికి స్ట్రాంగ్ ఫీల్డ్ ఉంటుంది. అండ్ ఇఫ్ ఇన్ కేస్ స్ట్రాంగ్ ఫీల్డ్ తీసుకున్నాం అనుకున్నాను, ఏముంటాయి నాన్న స్ట్రాంగ్ ఫీల్డ్? సైనైడ్, NO2, CO, అంతే. NH3 ఒక్కసారి ఉంటుంది. దేనికి నాన్న అది? అది కూడా కోబాల్ట్కి మాత్రం ఇట్ విల్ బిహేవ్ యాజ్ ఎ స్ట్రాంగ్ ఫీల్డ్ ligand. ఇంకా కాకుండా ఇంకేముంటాయి నాన్న వీక్ ఫీల్డ్ కి స్ట్రాంగ్ ఫీల్డ్? ఇంకా చాలా ఉంటాయి, బట్ మనకు అన్ని అని అవసరం లేదు, మీరు కూడా గుర్తుంచుకోవడానికి కష్టమైంది. But remember the another point here for 4D series and 5D series. So 4D series ki 5D series ki matram each ligand, every ligand is a strong field ligand. Every ligand, each ligand is a strong field ligand. So definitely their Hund's rule, it doesn't follows. The electrons will pair it up together in the 4D series and 5D series. Most of the complexes are D to sp3, the inner orbital complexes in case of 4D series and 5D series. That I will tell you later on. So see here. So you can understand here. So now this is a cobalt, so it is a strong field ligand, and these two electrons are paired up together, and here six electrons will be doesn't follow Hund's rule, so it will feel like this. Again the six vacant orbital will be formed like this. So six again vacant orbitals are produced here. Now you will get D to sp3 hybridization. So definitely the D to sp3 hybridization means this six ammonia ligand will come here, will come and it will make bond with this. So it will make a bond. The electrons will donated into their vacant d orbital like this. So each ligand will donate it two lone pairs. రెండు ఎలక్ట్రాన్లను ఒక్కొక్క దానిలో ఇక్కడ ఒక అమోనియా, ఇక్కడ ఒక అమోనియా, ఒక్కొక్క అమోనియా వచ్చి దాని ఒక ఎలక్ట్రాన్ పేర్లని ఈచ్ ఆర్బిటాల్ కి ఇస్తుంది. ఈచ్ హైబ్రిడ్ ఆర్బిటాల్ కి ఇస్తే అండ్ ఇట్ విల్ ప్రొడ్యూస్ this D2sp3 hybridization. So this you should remember these things here. Now what is the geometry here? 6 means generally it is a octahedral geometry. So remember these points here. So these are all these are all inner orbital complexes, and they are producing D2sp3 hybridization. So once again I am telling you, see here. So once again I want to tell you one thing here. So remember these things. So I will write here. So see here. So once again I am telling you, see here. So once again I'm telling you, see here. For the weak field ligand, so I will write bigger so that you can easily understand. So weak field ligands, and strong field ligands. So what are the weak field ligands? So simply H2O and halogens. Halogens are nothing but, what are the halogens here? So the halogens are simply all halogens like fluorine, chlorine, bromine, iodine, and the simple example that is NH3. And this is only applicable for the 3D series. ఇది 3D series కి మాత్రమే నాన్న. That is scandium to zinc. Remember this for the weak field ligands. So what about the strong field ligands? That is the cyanide, NO2, and simply the CO, EN, oxalate. So these are all. And ఇందులో కూడా మీకు ఎక్కువ రావు నాన్న. Mostly cyanide and CO తప్ప వేరే ఏం రావు. And this is only for the 3D series. 3D series ki వీటికి మొత్తం strong field ligand. But for the 4D series and 5D series, 4D series, 5D series, all ligands are strong field ligands. All ligands are strong field ligands. So that you should remember this. So for the 4D series and 5D series, so you know that which one is 4D series and which one is 5D series. So below the 3D series and 4D series, so below the 3D series, again the 4D series and 5D series are there, and they are completely whatever the each ligand, even the water is also strong field ligand with 4D and 5D series. Simply if you take palladium and platinum, you can take water, halogen, these can behave as a strong field ligand. And now there is also an exception. ఒక exception కూడా ఉంది నాన్న. That exception also I already told you just now also. So only the NH3 actually it is a weak field ligand, but in case of 3D series it behaves only at copper. ఒక కాపర్ దగ్గర బైండ్ అయినప్పుడు కోబాల్ట్ దగ్గర బైండ్ అయినప్పుడు it will behave as a strong field ligand. That is one exception. And remember this. And so again you should understand one thing here. So if it is weak field ligand, so it follows Hund's rule. It follows Hund's rule. Hund's rule ఖచ్చితంగా ఫాలో అవుతాయి నాన్న. Hund's rule ఫాలో అవ్వడం అంటే the electrons will fill like this. Once again I'm telling you that because it is very very important. 6 electrons ఉంటాయి, ఇలా fill అవ్వాలి, ఇలా fill అవ్వాలి. So this is the actual rule which is for the Hund's rule. అది Hund's rule కు actual rule నాన్న. But in case of the strong field ligand ఆ రూల్ వర్తించదు నాన్న. సో ఇట్ డజంట్ ఫాలో, హున్స్ రూల్ ని అసలు ఫాలో అవ్వదు, మొత్తానికి ఫాలో అవ్వదు. సో those 6 electrons will feel like this. సో అదే 6 electrons ఇలా ఫిల్ అవుతాయి నాన్న. ఎలా ఫిల్ అవుతాయి అంటే see here 6 electrons 1 2 3 4 5 6. సో in this way those 6 electrons will fill like this. ఇక్కడ d6 electron ఇలా ఫిల్ అవుతాయి. అండ్ హున్స్ రూల్ ఇవి మోస్ట్లీ ఏ కాంప్లెక్సెస్ ఎక్కువ వస్తాయి నాన్న, ఏ కాంప్లెక్స్ ఎక్కువ వస్తాయి అంటే మోస్ట్లీ ఇక్కడ హైబ్రిడైజేషన్ స్ట్రాంగ్ ఫీల్డ్ లిగెండ్స్ ఉన్నప్పుడు ఏమైతే అన్ని పేర్డ్ అవుతున్నాయి. సో 2 ఆర్బిటాల్స్ వేకెంట్ అవుతున్నాయి ఎక్కువ. సో అందుకే జనరల్లీ ద హైబ్రిడైజేషన్ విల్ బి D2sp3 ఎక్కువగా వస్తాయి అన్న, మోస్ట్లీ వస్తాయి, ఖచ్చితంగా వస్తాయని చెప్పట్లేదు. సో మోస్ట్లీ విల్ గెట్ D2sp3 hybridization, that is the outer orbital complex, sorry, inner orbital complex. So you will get only inner orbital complexes, mostly you will get like this. And if you take the this weak field, so ఇక్కడ అంతా ఫిల్ అయిపోయినా అన్న. సో అప్పుడు ఈ 3D మొత్తం ఫిల్ అయిపోయినాయి అనుకోండి, నెక్స్ట్ ఏముంటుంది అన్న 4s 4p 4d. that means this can mostly form sp3d2, that is the outer orbital complex. So here it will form outer orbital complex, but here in case of strong field ligand it forms as a inner orbital complex, inner orbital complex form అవుతుంది అంతే కదా. సో that is very very important here. And after this I want to tell you one thing also, another thing also, but I will tell you later so that you will feel some confusion in this. So after this is enough for this session, and now I will tell you the next session, that is the outer orbital complex. So till now we have completed the octahedral complexes with weak field ligands. So sorry, the complexes which are inner orbital complex. So now after that in the next session I will tell you the outer orbital complex here. So let us see here.